start sharing the screen. So our next speaker will be Andrew Swan from the UCL, and he will be talking about collision in white dwarf debris disks. So you're muted.
There we are. You can hear me now. Hi, everyone. Good to see you. I'm going to be talking about some work that we've been doing at UCL over the last couple of years. My collaborators are Jay Farihi, and we've had help from Tom Wilson and more recently Scott Kenyon. So when a star dies and becomes a white dwarf, it doesn't necessarily lose its planetary system. And we do believe that most stars carry planetary systems with them. So there's evidence for this around white dwarfs from a number of observational properties. So the first is that because of the high gravity of white dwarfs, they should only display hydrogen or helium at their surfaces. But at 50% of white dwarfs, or up to 50%, we see metal lines in the spectra. And these have to have an external origin. So the story goes that an asteroid is perturbed onto a highly eccentric orbit, passes within the stellar rush limit, and is tidally disrupted. It then leaves a disk of debris behind that gets accreted onto the star. And this is where we see the metals from. So we also see the debris. I think the most intuitively understandable signature of that is, oh, sorry, pardon me. I should have said the metals that we see in these stars are mostly rocky material. So that, that matches up with the disrupted asteroid story. Anyway, as I was saying, we see transits from debris that passes in front of the star. There's a handful of cases of these, but given the geometric low probability of getting exactly the right alignment, it suggests that many systems have orbiting debris. And we see evolving transits in the light curve, which suggests these are not solid objects, but debris clouds. What happens when these are not lined up favorably? Well, we can still see them through their infrared emission. And in this little cartoon here, I've made an SED of a dusty white dwarf. On the left, we have a black body representing the star. It's hot, so it peaks in the optical. And on the right, we have a black body representing dust at 1000 Kelvin or so. Now, notice that the y-axis is logarithmic. So when you're looking at these things in the mid-infrared, say around 4 to 5 microns, the difference between the stellar photosphere and what you actually observe can be a factor of several. So we're able to see these debris disks through their excess infrared emission. And dozens of these systems are known. Among them, a small subset also show emission lines from gaseous debris. Now, these double-peaked emission lines indicate that the material is orbiting very rapidly, and that's consistent with orbits within the rush limit of the white dwarf. So the dust that we see in the infrared and the gas that we see in these emission lines are linked. So why do we care at all? Well, the metals that we see in these stars tell us about the building blocks of rocky planets, and that's bulk compositions, for example, that we can't get from any other observational source at the moment. But once the metals are in the star, you can't tell much about where they came from. So the debris disks are kind of one step back in that process, and they can perhaps tell us something about where in these systems this material comes from. And that's why understanding these disks is useful. So for the last couple of decades, there's been a fairly standard model for describing these disks, and that is of a flat, compact, optically thick disk close in around the star. And a good picture to keep in your mind is Saturn and its rings. So white dwarfs are planet-sized, and we have this razor-thin ring of debris around them that's opaque, so optically thick, and not much happens to Saturn's rings. They're a quiet environment. There are dynamical effects there, but for the large part, they don't do much. Now, in the white dwarf version of this, these optically thick disks successfully reproduce the photometry that we see at many of these systems. But they have some other benefits that has made them quite attractive as a model. So in the stellar photospheres, we see enormous quantities of metals in some cases. So minimum masses that are equivalent to the largest asteroids in our solar system or moons of gas giants. And the accretion rates that we see suggest that these accretion events are feeding the stars over perhaps up to 1 million years. So you really want a model that can last that long and supply that much mass. And the opaque disk is attractive because it has those properties. So unshielded dust, optically thin dust, has Poynting-Robertson drag acting on it, and it will be pulled in towards the star on a short time scale, like decades maybe, compared to these perhaps million-year lifetimes. Whereas the optically thick disk is self-shielding and only loses mass at its inner edge. And also, you can hide lots of mass inside the optically thick disk without increasing its emitting area. So that's all very well and good, but there's been indications that the standard model is not quite perfect. So in one case, and we're looking at a real SED now, not just a cartoon, you see this feature at around 10 microns. Now, there's only a handful of stars where these observations have been made so far, but they all have this emission feature. And this comes from silicates, and they have to be optically thin to generate this feature. So we know already that there's at least an optically thin component to these disks. But more troublingly, a recent paper has shown an example of a star where the standard model simply fails to reproduce the observations. So the observations are here in these red points. The stellar photosphere is represented by the blue line. And if you add to that the black line, which is the kind of brightest standard disk that you can generate, you fail completely to match up with the observations. And then the final nail in the coffin, as it were, is the phenomenon of infrared variability, which is not predicted by the standard disk. So over the last few years, people have been noticing that these dusty systems vary in the infrared, but not much had been done systematically beyond the first couple of observations. So this is where our team has been working. And to look at the infrared, you need to go to space, really. So a couple of telescopes have been pivotal in our understanding of these debris disks. And on the left, we have WISE. On the right, we have Spitzer. So WISE has been conducting an all-sky survey over the last decade or so, and it covers the whole sky once every 6 months. So every white dwarf that is bright enough to be seen has got a decade-long light curve in WISE. Spitzer, meanwhile, only targets white dwarfs when people ask it to. So while it's a more capable instrument, there's perhaps not the same coverage as WISE has. So to investigate this variability phenomenon, the first question to ask was, is it widespread? And this was a question that we addressed using the WISE archive, dug out all of the light curves and simply asked, are the stars varying? And the answer was, yes, they are. So here in blue, we have the dusty white dwarfs, and in gray is a control sample of non-dusty white dwarfs of similar magnitudes. And you can see the x-axis is signal to noise, and the y-axis is the significance of the variation you find in the light curve. And as you can see that as you go to higher signal to noise, the variation becomes more and more obvious, and the white dwarf population lifts off and departs from the comparison stars. So we've established that the population as a whole are varying in the infrared, but WISE is not the best of instruments to use. And this slide from the first infrared variability paper neatly demonstrates why. Spitzer has much better sensitivity and resolution, and it can see contaminants that you can't easily distinguish from WISE. So to do real work, you need the capabilities of Spitzer. But as I mentioned earlier, Spitzer only looks when you tell it to, and no one had really been investigating this phenomenon directly. But that doesn't mean that there wasn't plenty of archive data to work with. So we dug out all of the observations of the dusty white dwarfs over the years, added another point to the light curve with a kind of a snapshot campaign, and repeated the analysis. And this time, with the better sensitivity, you can get more interesting results out. So this plot summarizes the findings. On the bottom is the baseline, so the time between a pair of observations, and up the side is the flux change that you see. So you see that for short timescales, there is really not much coverage, and there's no significant variation. But as you move to timescales of months towards years and decades, you see these darker points appear, and these are where you get significant variations. And the longer the baseline, the larger the flux changes you see. And there's no preferred direction for this. The flux can go up just as often as it can go down. And perhaps the most interesting point on this plot is these square points, which correspond to the dusty systems which also have emission from gas. So we found not only are all of these stars varying, but that there's a correlation between the presence of gas and the strength of the variation. And the process that may well link these is collisions. So I mentioned this gas that we see around some of these stars earlier. You can generate it either through sublimation, where dust gets too close to the white dwarf and is heated until it becomes gas, or you can generate it in collisions. Now, collisions also will liberate lots of dust, And if that dust is optically thin, it will increase the emitting area and you will have an increase in flux. So putting the two together seems quite an obvious thing to do. And as luck would have it, as this paper was being wrapped up, a new discovery was announced, and there was a so-called infrared outburst at a dusty star. Now, the flux changes there would be completely off the scale on this plot. And I will show you the light curve. So this is the WISE light curve in both of its channels, and we can see that for the best part of a decade, nothing happens. The star has a modest excess, but no interesting features really pop out. But suddenly, the star brightens between one observation and the next. So within 6 months, it's more than doubled in brightness. And it continues to do this until 2019. And at this point, the paper came out and announced this. And we realized that we had one more chance with Spitzer before it retired to get observations of this star. And we had a few days to turn this around. So that's what we did, and we got the observations. And these are shown in the red and blue points. So zooming in on them, we see this nice decay trend. So the flux is now coming down from its peak. But the interesting point on this light curve is that there's bumps. So you can see, I think the best example is here. We've got this increase in flux correlated in both of the channels that's overlaid on the general downtrend. And perhaps another one here, maybe another one here. So this fits nicely in with the model of a collisional cascade, where you have a swarm of debris around the star of various sizes, and the objects encounter each other now and again, and they collide, produce more debris, and the whole thing grinds itself down. So you're generating lots and lots of dust, which is being ground down and perhaps turning into gas at the very smallest sizes. And meanwhile, the larger objects are producing larger collision events. And the whole thing reaches an equilibrium where everything is distributed in a power law size distribution. So you have many, many small collisions between small objects and occasional collisions between much larger objects. And it's these occasional large collisions that we think are responsible for these bumps in the light curve. So if they're infrequent enough that they occur stochastically on your, say, 2-day sampling cadence, and they produce enough material to make this bump in the light curve, then the model works. And I have a paper on the verge of submission where we've shown this with a simple theoretical model. Now, I haven't mentioned this yet, but not only is this star the most variable of all in the infrared, but it also has gas emission. And this fits with the correlation that we found for the wider population. And so I would argue that this star isn't special. It's simply being seen at a special time. And while it might be the most active today, another star might take its place tomorrow and become more active. So the whole population is probably evolving collisionally like this and producing lots of this optically thin dust. Now, there are issues with that, but the overall picture is that you don't necessarily even need the standard model of the opaque disk anymore if you've got this constant generation of optically thin dust. So it remains to be seen whether you need both or just one. But for the moment, it looks like collisions are an important process in white dwarf debris disks that generate both the variability and the observed gas. And just to convince you that this outburst star isn't necessarily special, I'm going to compare it side by side with a different star's light curve. And we can see they look very much the same as each other. You've got this decay curve. And in the second star, we can see a bump in the light curve, just like on the left here. The only difference is that this one is on a timescale 100 times longer than this one. And the collisional cascade is thought to follow a 1/t flux decay. So these two probably sample that same curve, just at different timescales. So we're out of time, and I'll leave you with my summary. White dwarf debris disks are variable in the infrared in a way that's incompatible with the flat disk model. We think collisions are generating dust and gas in these systems, and that this is the source of the variation. And with that, I'll take any questions. Thank you.
Yes, thank you very much, Andrew. Let's wait until questions pop up. Sandro is asking, he says, yeah, thank you, nice talk. What are the implications of these collisions on the lifetime of debris disks?
That's a good question. I'm not sure I can answer it very sensibly, but I think the main question is, where is the material coming from in the first place? Are we getting continual input from the wider system to maintain these collisional cascades, or is the material present there to start with and we only see it once it's underway? I don't have a very good answer for this, and I have to say that estimates of debris disk lifetimes range from years up to millions of years, so that this is really one of the main questions for debris disk research at the moment.
Okay, then Tom is asking if you see any color variations in this target.
Yeah, so unusually, that infrared outburst star did have color variation, which is not normally seen. Typically, the variability is all with the same color, and that means that the dust is at the same temperature. But in this instance, it looks like we had a temperature change. And I think the reason for that could be that if material had been in one of these optically thick disks and was then kind of, and then it had a whole load of optically thin material added to it, the optically thin material has a higher temperature because it's not shielded from the starlight. So that's what we could have been seeing. But with only 2 photometric bands, it's a little difficult to draw detailed conclusions there.
Okay, then the next question is if you could discuss what sort of collisions you are currently thinking of. So collisions between what?
Okay, so think about asteroids, say. This is how our own asteroid and Kuiper belt have evolved. You just have things that are roughly co-orbital with each other occasionally meet and collide destructively. So the orbital velocity is near a white dwarf are hundreds of kilometers a second. So if these things are even slightly misaligned in their orbits, then the collisions will be destructive. Okay,
then I think we take one last question, which by Boris, and which I think relates to that a bit. Do you prefer collision between bodies already orbiting the white dwarf, or could you have a newcomer coming in from far out, like in the Jura 2008 paper suggested?
Honestly, I think both are viable at the moment, and this is an open question. There's been some recent work by Uri Malamud that discusses what happens when new material intersects with an existing disk. And it looks like that material generates gas and circularizes quickly. So that could then leave you with objects already orbiting the star for the next generation. So I think this is an open question at the moment, and this is really where the theorists are going to have to focus their efforts, and hopefully the observers can catch up with them once we get a new telescope to play with.
Okay, then thank you very much for your talk. Again, a lot of more questions showed up. Maybe you can stay, and the people who had the question can then look out in which breakout room Andrew ends up, and then talk to him and keep on discussing. Yeah.